Hey everyone, we're going to take a look at some more gas laws that are going to govern how gases behave. In the previous lecture, we saw Boyle's law was a relationship between pressure and volume. We saw that they're inversely related, meaning that if pressure goes up, then volume goes down, or if pressure goes down, then volume goes up. So we have this gas law that stemmed from it right here, the P1 times V1 equals P2 times V2. We also saw in the last lecture, Charles has a law about gases as well. He took a look at volume and temperature, and he found that they're directly related. So if you have an increase of temperature, you're going to increase the volume. If you have a decrease in temperature, you'll decrease the volume. And that is depicted with this one right there. So V1 divided by T1 equals V2 divided by T2. So what if these two variables changed at once? Then we have what's called the combined gas law, where we combine both Boyle's and Charles' law into one giant law that apparently got really screwed up when this app uploaded my PowerPoint. So what it should look like right there is P1 times V1 over T1 equals P2 times V2 over T2. Oops, that should be a 1. What am I doing, Mrs. Carrillo? All right, here we go. So this is what we call the combined gas law. When we take a look at pressure, temperature, and volume all at the same time. Okay, so this law can apply when the amount of gas stays constant. So that means that there's no leaks inside the container that we're looking at. Before and after we apply, different pressures, temperatures, or volumes. So we've got no leaks, no excess gas coming in, no excess gas, leaking out of the system. It's a sealed container. And you have to remember, okay, this is going to be the thing that is going to get you in trouble the most. It's going to get the wrong answers. You must make sure that you use Kelvin as your temperature every single time. You cannot use Celsius. Okay, in fact, here I'll put a little degrees Celsius and I'll put a big red X through it. You cannot use degrees Celsius. You must convert degrees Celsius to Kelvin. Okay, so you got to convert it to Kelvin, and to do that, Kelvin is whatever you have in degrees Celsius plus 273. So add 273 to whatever temperature you're given in degrees Celsius to make sure you turn it into Kelvin before you put it into this, to any of these gas laws. Okay. All right, so let's take a look at an example where we are going to use this gas law. This example says, suppose a person carries a cylinder with a movable piston that has an initial volume of 3.65 liters up a mountain. I'm not sure who the heck would actually do this, unless, of course, maybe you're a construction worker, but otherwise I'm not sure anybody would bring a cylinder with a movable piston up a mountain, but hey, there you go. All right, so the pressure at the bottom of the mountain is 755 millimeters of mercury. And the temperature is 302 Kelvin. The pressure at the top of the mountain is 687 millimeters of mercury, and the temperature is 291 Kelvin. What is the volume of the cylinder at the top of the mountain? Okay, so basically, what we want to do is these questions are going to get kind of lengthy because they're going to give you a whole bunch of information. And if we look at our combined gas law, we need a whole bunch of information because we need pressure and temperatures before and after, and we need to figure out what we're going to be solving for. So we have 6 variables in this equation, so we need to basically be given 5 out of the 6. So we need to make sure we're reading very carefully. Okay, so when we're working with these gas laws, we're going to be be given a initial scenario versus a final scenario. So like a before picture and an after picture, and then we need to put them in the correct sides on the whatchamacallit, the equation. Okay, so we can kind of think of the P1 side as our before side, right? And then the 2 side is kind of like our after picture. So this is the after side. So we take a look in reading, we see the word initial. So that's going to be the initial volume. So that's going to be our V1, right? And it says the pressure at the bottom of the mountain. So that's, again, what we start with is 755 millimeters of mercury. So that's going to be our P1. And the temperature is 302. So that's going to be our T1. So we're given V1, P1, and T1. And then we've got, it says the pressure at the top of the mountain. So that means we've climbed the mountain and we got there. So this is our after picture. Is 687 millimeters of mercury. So that's our P2. And the temperature is 291 Kelvin. So that's our T2. So we're given P2 and T2, and it's asking what is the volume of that cylinder at the top of the mountain. So in this equation, we're going to be solving for V2, right? So we're given all the variables except for V2. So there's always more than one way to solve these types of problems. Mathematically speaking, we can do, you could either cross multiply, right? So you could do like P1 times V1 times T2 equals P2 times V2 times T1, and then you could solve for V2, okay? Or you can, do the whole algebra thing where you get, V2 on this side by itself, by first multiplying both sides by T2, right? And then you would divide by P2 on both sides to get V2 by itself. Either one works, okay? So if you understand cross multiplying and solving for the variable, do it. If you need to do it, algebraically by just isolating V2 using algebra, dividing and multiplying both sides by the different variables in order to get V2 by itself, that works just fine too. Okay, you'll get the same answer either way. So let's start plugging these things in to this equation. All right, so we've got our P1 is 755, okay, millimeters of mercury. We can see that we have millimeters of mercury for both the before and the after picture, so that means we don't need to convert those to anything else, okay? As long as you're working with the same unit on both sides, you're good. Now, if one of them said millimeters of mercury and the other one said atmospheres, then you'd have to convert one to the other, okay? So just keep that in mind. There's only one gas law that we're going to see, that you have to use specific units, okay? And this is not the one. So we have our P1, and then we have our V1. Our initial volume is 3.65, right? And then we've got our T1, which is 302 Kelvin, okay? And so that's that side. And then we're going to put the other information on the other side. So we have our P2, 687, right? We're solving for V2, so that's our variable. And then we have our T2, okay, the temperature at the top of the mountain, 291 Kelvin, okay? All right, so we're going to go ahead and cross multiply or solve for V2. We are going to get an answer of 3.86. Okay, so V2 is going to equal 3.86, and we do need to make sure that we use our units, and for volume, it is liters. We can see up here in the question that liters is in our unit for volume. Okay, so 3.86 liters. So at the bottom of the mountain, the cylinder was 3.65 liters. At the top of the mountain, with the pressure and temperature changes, the volume of that piston is now 3.86. All right, so please make sure you do that math on your own so you do understand how that works, and so that you get the correct answer for that. All right, here is another one that you can try. Please do try this on your own. So pause the video right now, try it on your own, and then you can play it again and I'll show you the answer. But I do want to make sure that you guys recognize that right now this is giving you degrees Celsius, okay, and so you have to make sure that you turn these into Kelvin. Okay, so that's the only unit you need to make sure that you turn, that you convert to Kelvin. Otherwise, as long as we've got, like, for example, milliliters on both sides, right? Then, and we're going to be solving for millimeters of mercury, which were given in the beginning as well. So all the other units are good, but you do need to make sure that you convert that degrees Celsius to Kelvin. Okay, so go ahead and pause it, try this one on your own, and then unpause it, and I will show you the answer. All right, so here is the answer. We've got a pressure of 1,250 millimeters of mercury. Okay, you can see my work here. So we've got the P1 times V1 over T1 equals P2 times V2 over T2. Down here in red, I plugged in all of the variables in the right spots, making sure I turn degrees Celsius into Kelvin. And then in green, I solved for it. So I just cross multiplied. I did 735 times 158 times the bottom of the other side, 358. And then I said divided by 108 times 307. And then in the end, I got like 1,253.9 something. All right, but if I take a look at the math that I actually did up here, okay, I can see you've got 3 sig figs for everything. You might go, hey, we only have 2 sig figs up here, but remember, we do need to convert that into Kelvin. And when we do that, we use the, when we're adding, we use the lowest number of decimal places. Since neither of them have decimal places, 273 versus the 85 or the 34, it's going to be rounded to the whole number. And so we'll use that whole number as a basis for the amount of sig figs when we're doing our math. So we can see when we're doing the math here, all of them have 3 sig figs. So that means we need to round our answer to 3 sig figs. Okay. So hopefully you guys understand what's going on with the math in doing this type of problem. If this is still, if you still need practice, then please go ahead and go back to your textbook and do lots more practice problems with this combined gas law. Because guess what? We're moving on to another gas law. We've got a ton of gas laws that we're going to be utilizing. So you got to get them all straight in your head. We got Charles' law, which is volume and temperature. Boyle's law, which is pressure and volume. We had the combined gas law when we combined all 3 of those together. And now we're going to take a look and throw in moles as well. Okay, so we're going to be taking a look at Avogadro's law, which is actually one of the first gas laws. Avogadro was in the 1700s a French scientist, I believe. Maybe? I don't remember, honestly. But he was a scientist that worked with gases. In fact, he was the one who came up with the mole number of 6.02 times 10 to the 23rd. All right, so he did that by investigating and working with gases. And so another thing that he figured out was the relationship between the number of moles of a gas and its volume. And this one is actually really simple. So this is the relationship between volume and the number of moles, and it is linear. Okay, so as the number of moles increases, the volume increases. All right, so it's kind of intuitive, right? So you blow up a balloon with air, the more moles of air you put in, the bigger the balloon gets, right? And if you squeeze out moles of air, the volume decreases. So this one's actually really, really simple. And that's why it was one of the first. So this law holds true as long as pressure, temperature of the gas are held constant. So we're not changing the temperature or the pressure of the system at all. So in this case, we've got this equation here, V1 over N1 equals V2 over N2, where we've got the volume and the moles being directly related to each other. So here's an example of a question that you might run into while working with Avogadro's law. It says, a 4.8 liter sample of helium gas contains 0.22 moles of helium. How many additional moles of helium gas should you add to the sample to obtain a volume of 6.4 liters? Assume that there's constant pressure and temperature on the system. Okay. So we're starting with 4.8 liters of helium gas and 0.22 moles, right? So that's our V1 and our N1. So if we write out our equation first off, we have V1 over N1 equals V2 over N2, right? So we are going to put our V1, our volume, 4.8 liters on top, and the moles on the bottom, 0.22 moles on the bottom. And that is going to be equal to, as long as we keep our pressure and temperature constant. On the other side, right, so we've got our final volume, 6.4 liters, and we've got, how many moles is that going to be, basically? So that's our N2. And so if we solve for N2, cross multiply, we'll get 6.4, right, times 0.22 equals 4.8 N2. And so we divide by 4.8 on both sides. And in the end, we'll get N2 equals 0.29, right? So that's how many moles we'll have in the end. But we do need to be careful with this question. It says how many additional moles? Because remember, we started with 0.22, and then this is going to be our final volume, 0.29. So that means we need to add not the full 0.29, but we need to add whatever, 0.29 minus 0.22. So 0.07 additional moles is what our answer is. Okay, so again, how many additional moles? 0.07 moles we need to add to this in order to get up to the right volume and number of moles. Okay, so pretty simple little gas law here, comparing the volume and the number of moles. All right, so again, here's one for you guys to try. So go ahead and I'll read through it and give you any hints if need be, and then you guys will pause, do it on your own, and then you can play it again, and I will show you the answer. Okay, so it says a chemical reaction occurring in a cylinder equipped with a movable piston produces 0.68 moles of gas product. Okay, so that is our ending moles, so that's our N2, so that's our product. If the cylinder contained 0.11 moles of gas before the reaction and had an initial volume of 2.1 liters, what is the volume after the reaction? So we are going to try to find V2 in this whole thing, right? So remember, our equation is this, okay? And we're given the 3 out of the 4 variables, so you need to solve for V2. So go ahead and pause, do that, and then you can unpause and check to make sure you're correct. All right, so hopefully for your answer, you got 13 liters. It seems kind of big, going from 2 liters to 13 liters, but remember, look, we started with only 0.1 moles and we went up to almost 0.7 moles. So that's a 6 times fold, so 2 times 6 is about 12, so 13 is pretty, reasonable answer. Okay, so 13 liters. Again, on your calculator, you probably got 12.98 something, 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 but remember, sig figs, we've got 2 sig figs for everything on here. So we're going to round that to 2 sig figs, which is 13 liters. All right, so once again, if you need extra practice with this or extra, explanation, please visit that section in your textbook for Avogadro's Law. All right, so we've come to what's called the ideal gas law. So this is kind of the big gas law that most scientists kind of use pretty regularly if they're working with gases. This ideal gas law is basically kind of a combo of all of them. So we have Boyle's law, remember, that said volume is inversely proportional to pressure. So if the pressure goes up, the volume goes down. If the pressure goes down, the volume goes up, right? We had Charles' law that says volume and temperature are directly proportional or related to each other. And then we had Avogadro, who said that volume and moles are directly related or proportional to each other. Okay, so we're going to basically combine those, all three of them. So the combined gas law we saw before was just for temperature, pressure, and volume. Now this ideal gas law is for adding moles in there as well. Okay, so if we take all three of these and we put it and combine it into one equation, we're going to see that V is equal to N times T over P, right? Because we have P on the bottom right here in this. We do have this R here that's kind of like, wait, where'd that come from? This R is a constant. Okay, so when doing experiments, whomever, I don't even know who discovered this, but whoever that scientist was saw that that he had to multiply the equations by kind of the same number every single time. So he called that a constant, and this constant is this number here, 0.0821. And this, if you guys remember earlier, I said there's one gas law where you have to use particular units, and this is the gas law. Okay, so this ideal gas law is the one where you have to make sure that you use the units liters, atmospheres, and Kelvin. Okay, and that whatever volume or mass is in moles. Okay, so you got to use moles, not grams or anything like that. Okay, so this is very particular. So we have to use liters, atmospheres, and Kelvin for the pressure, volume, and temperature. Okay, so kind of as if we kind of rearrange this equation so it's nice and clean, linear in looking, we can say PV equals nRT. Okay, so pressure and volume is going to be equal to the moles times the temperature times proportionality constant R. Okay, so in kind of short terms, scientists call this what we call the PIV-NERT, gas law, or the ideal gas law. All right. In this section of your textbook, the author talks about aerosol cans and, what happens if you heat them up. And, this is, as a high schooler myself, something that, people would, try to do at big bonfires at the beach. You bring an aerosol can, set it next to it, and see if it explodes. Fortunately for us, they never did. But that's a good thing because that could have done a lot of damage to people standing around. But, stupid kids. But please don't try that. It was really dumb in hindsight. This ideal gas law kind of explains why. If you increase temperature, you're going to increase the volume and the pressure. And increasing volume and pressure, is going to make things explode. So do not put any aerosol cans or cans filled with any kind of gas. That's what aerosol means. Cans filled with any kind of gas near a heat source, because these gas molecules can start moving so fast that they can actually explode the container that they're in. So there's a little, what do they call it? PSA, public service announcement for you. Don't do this. All right, so back to the ideal gas law, or the PIV-NERT gas law. All right, so if we've got this, PV equals nRT, we can, if we've got values for any one of these four, we can figure out the other, if we have values for any of the three, we can figure out the fourth variable in this problem, okay, just like any other algebra problem, okay. But like I mentioned before, and I'm going to mention it again because it is very important, when using this one, you must express these variables within the units of R, which is our proportionality constant. So we have to have pressure has to be in atmospheres. Volume has to be in liters, right? And temperature must be in Kelvin. And we're working with N, it's got to be in moles, not grams. Okay, so you got to use your periodic table to convert grams to moles if need be. Okay, so got to use those units. So let's take a look at a few of these examples. So the biggest thing that you're going to see in examples like this is that these types of gas law questions are not going to give you a before and after picture. Okay, so they're kind of really easy to spot. It's not a little scenario where you've got, a movable piston going up a mountain that has this, and this before, and this, and this after. Nope, that's going to be your, combined gas law or Charles' law, Boyle's law, Avogadro's law, any of the ones that we talked about before. The Pivnert, or the ideal gas law, is just going to give you, information about 3 of the 4 variables, and you have to discover the 4th or solve for the 4th. All right. So when you're reading something, if it's giving you a before and after, you're not going to use this ideal gas law. So it's kind of a little trick of the trade there. Okay. So here's a couple of examples. First one, what is the pressure of 0.18 moles of gas in a 1.2 liter flask at 298 Kelvin. Well, luckily for us, we have all of the correct units, so we just need to plug it into our Pivnert or ideal gas law. PV equals nRT, right? So we are being asked to find pressure, so we need to solve for pressure. So first thing, let's divide both sides by V. So pressure is going to equal nRT divided by V. So we'll put in all of our values for nRT and V, and we will then solve. All right, so N is 0.18 moles. Okay. R is our constant, 0.0821, and that is mole liters over atmosphere Kelvin. Okay, and then we've got our temperature, which is 298 Kelvin, and then we'll divide that all by our volume, which is 1.2 liters. Okay. All right, so taking a look real quick. Oh, okay, so I messed up a little bit in the units for this. Okay, so because the units for, if you can follow the units, you can then you kind of doing the math right. Okay, so we need to have moles on the bottom and atmospheres on top. So atmosphere times liters over moles times Kelvin is the units there for R. Okay, so when we actually do the math for all of this, right, so we take our 0.18 times 0.0821 times 298, and then we divide it by 1.2, okay, we are going to get 3.7, and our pressure is going to be in atmospheres. So 3.7 atmospheres, okay, is our answer there. And one of the ways we can tell what our unit is going to be is because the units that we have plugged in should cancel with each other. So for example, we've got Kelvin here and Kelvin on the bottom here, so we multiply them top, bottom, they cancel, right? So we've got moles on top here, moles on the bottom there, so when they multiply, it cancels, right? So we have liters on top, liters on bottom, cancel. So what we're left with is atmospheres. So that's what I was saying before. that knowing the units in the right order is going to help kind of figure out what our unit is in the end, making sure we do the math right. Okay, so 3.7 atmospheres is what the pressure of this system is at. All right, so let's take a look at the second example. So this says calculate the volume. So this time we're going to be solving for V, occupied by 0.845 moles of nitrogen gas at a pressure of 1.3 atmospheres and 315 Kelvin. So again, our equation here is PV equals nRT. And we're going to plug everything in. So we've got our pressure of 1.3. Oh, actually, first, let's solve for V. So we're going to solve for V, so we're going to divide both sides by P. So our equation is going to end up being V equals nRT divided by P, right? And so here we can plug it all in. So N is 0.845 moles. And then we've got R, that's our 0.0821 atmosphere liters over mole Kelvin. And then we have our temperature, 315 Kelvin. So far everything's in the right units. Good. And then we're going to divide by our pressure, 1.37 atmospheres, which again is in the right unit. So when we do that and we cancel all our units, so atmosphere, atmosphere, mole, mole, Kelvin, Kelvin, we should end up with our volume in liters, which is 16.0. Let me put that in darker. There we go. 16.0 liters is our answer. Okay. 3 sig figs. All right, so in our calculator we got 15.95. So to round it correctly, the 5 would bump up the 9, to 0 would bump up the 6, 5 to a 6. So 16.0, we need 3 sig figs in this answer. Okay, so again, hopefully this makes sense. Take it one step at a time. Try to solve all of these on your own, and then go back to see if you've got them correct. If you need any more help, grab your textbook and take a look at this section on ideal gas law. But before we head into the next thing, I do want you to try this one on your own. So, calculate the number of moles of gas in a basketball inflated to a total pressure of 24.2 psi with a volume of 3.2 liters and 25 degrees Celsius. Now when doing this one, look, psi needs to get converted to atmospheres first. Okay, so we've got, just remember, 1 atmosphere equals 14.7 psi. Okay, and then we also need to make sure we convert degrees Celsius to Kelvin, right, by adding 273. Okay, to our degrees Celsius. So make sure you do those 2 things first before you plug them into your equation. All right, so go ahead and pause, do this one on your own, and then come back for the answer. All right, so hopefully you got the answer, 0.22 moles. All right, so like I said, first you have to convert psi to atmospheres, so 24.2 psi equals 1.65 atmospheres. Got to turn Celsius to Kelvin, so 25 degrees Celsius is equal to 298 Kelvin. And then we can plug it into our equation. Now the equation was PV equals nRT, and in this we needed to figure out the number of moles. Okay, so moles is solving for N. So when we do that, we divide both sides by R times T. So here, N equals PV divided by R times T. When we plug them all in, we get 0.22 moles, and we have to round that to 2 sig figs because this here is the least amount of sig figs, 3.2. So that's 2 sig figs, so our answer needs to be 2 sig figs, okay? Just a quick note about sig figs, the R, the constant R, 0.0821, will never be used for determining sig figs. So even though we're doing math with it, it is kind of like a constant number, so it does not factor in when we're figuring out sig figs. So make sure you just don't look at R when you're trying to figure out the number of sig figs to round to. All right, so once again, number of moles, 0.022. All right, and now our last little bit for this lecture is still working with the Pivnert's or the ideal gas law, but knowing the fact that if we're working with moles in this equation, then if we're given grams, we could convert to moles. We could do a little stoich with it, right? So we could use this ideal gas law in combination with the mass measurements to calculate the molar mass of a gas. Actually, we're not doing stoich yet. That's the next lecture, gas problems in stoichiometry. Here we're just going to talk about the molar mass of a gas. So here it says a sample of gas has a mass of 0.136 grams, and its volume is 0.112 liters at a temperature of 298 Kelvin and a pressure of 1.06 atmospheres. Find its molar mass. So remember, molar mass is grams per mole. That's what molar mass means. It's the number of grams in a mole of the substance, right? So here we're given grams, so we're going to take our 0.136 grams and we're going to divide it by the number of moles of this gas. But of course we're not given the number of moles outright. What we are given is the volume, temperature, and pressure, so that we could use our PV equals nRT equation, solve for moles, right? And then we could take our moles and divide it by our grams to get the molar mass. So let's do that. So we're going to solve for N. So N equals pressure times volume divided by our R times T. When we plug in our numbers, our pressure is in atmospheres. Good. So 1.06 atmospheres times our volume, which is 0.112 liters. Divided by R, 0.0821 atmosphere liters, mole Kelvin, and then multiplied by our temperature, 298 Kelvin, right? So liters, atmosphere, Kelvin. We're going to end up with moles, and when we do the actual math with the numbers, let's see, we get 0.00485. Okay, so that's the number of moles in this gas sample. Okay, so remember, we're asked to find its molar mass, the grams divided by moles. So we're going to take this 0.00485 and we're going to put it right under there. So we're going to do 0.136 divided by 0.00485. And we get a molar mass of 28 grams per mole. Okay, so our answer is actually 28, should be 0.0 sig fig wise. So 28.0 grams per mole is the molar mass of this gas. Okay, and although it doesn't ask for it, we can figure out what actual gas this is. If this is a molar mass, then we can use that to identify the gas. So if we look at our periodic table, so grab a periodic table if you got it handy, or if you got your textbook handy, right there in the front cover is a periodic table. And if you look for the mass of 28, you'll see that there is no gas that is a mass of 28. But if you guys remember, we do have some diatomic gases. Some diatomic gases meaning that they are found as kind of like twins or two, like O2, oxygen, O2. Hydrogen, H2. Remember the Hofbrinkel? So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are those Hofbrinkel diatomic gases. Those are always found together as they're kind of twin. So if we divided 28 divided by 2, assuming that's a atomic gas, or diatomic gas, 28 divided by 2 is 14, right? Is there a element who has a mass of 14? Okay, so you should see nitrogen okay, does have a mass of 14. So this gas that has a molar mass of 28 is actually nitrogen, N2. Okay. So again, that's something that you're not going to be, having to do, but it's kind of a little extra step in using that molar mass to figure out the identity of the substance. All right, as always, here's one for you guys to try. So it's a sample of gas has a mass of 0.311 grams. Its volume is 0.225 liters, and it has a temperature of 55 degrees Celsius. Turn that to Kelvin first, right? And a pressure of 886 millimeters of mercury. Again, got to turn that to atmospheres, right? So 1 atmosphere equals 760 millimeters of mercury. Okay, so just as a conversion factor there. Determine the molar mass. So remember, the molar mass is grams divided by moles. Okay, so go ahead, pause, figure it out, and then you can push play and see if you're right. Okay, so hopefully you guys got a molar mass of 31.8 grams per mole. Okay, so you can take a look at the work there. I converted Celsius to Kelvin first, and then converted millimeters of mercury to atmospheres, right? Solved for N to find moles. Plugged everything in and got moles equal to 0.00978, and then took that moles and divided it by the grams that were given in the very beginning to get our molar mass. Grams divided by moles. So 31.8 is the answer for that one. All right, so we've come to our last slide here. And this is just kind of a little caveat slide, a little, hey, there's some exceptions to this rule slide. So basically, this ideal gas law only kind of really works for gases that are acting ideally. That's why it's called the ideal gas law. And what that means is that a gas that works or that is behaving ideally is one where the volume of gas is small compared to the space between them. So that means, that they've got lots of space in between them. They're really acting like gases, being far apart and moving fast, not, attracting each other and coming together sometimes as liquids. All right, and the force between the gas particles are not significant, again, meaning they don't have much attraction for each other. So they're behaving as gas particles should. So for our purposes, we're going to, unless it states otherwise, we're going to be assuming that all of the gas problems that we're going to be doing are for gases that are behaving ideally. But in reality, these assumptions kind of break down under either a super high pressure or super low temperature. Okay. So for example, if you are working in like refrigeration, then you can't rely on this gas law to kind of help figure things out, because you're working with too low temperatures, and gases at too low of temperatures start condensing, where their volume of the gas particles versus the space in between them breaks down. And if they slow down too much, then the force of attraction between the gas molecules pulls them together, and they start kind of maybe even condensing down into liquids or solids. All right, so these assumptions break down under super low temperatures or very high pressure as well. If you put gas under an immense amount of pressure, you're going to force the particles next to each other, and then this gas law does not apply. Okay, so that's just kind of a caveat, but you don't need to worry about it, because all of the problems that you guys are going to do, we're going to assume that the gas behaves ideally. Okay. All right. So once again, if you have any questions about this one, be sure to ask, or go to the certain sections in your textbook for more explanation and practice.